Hey everybody, this video is on chapter 3.4, Exponential and Logarithmic Equations. So we're going to talk about solving equations involving exponential expressions and logarithmic expressions. All right, so it starts on page 232 in the textbook. If you want to turn there and look at the opening for the chapter, I've written down some of the notes. Basically, when you solve exponential expressions, according to the textbook, it says on page, no, I got that wrong. That is page 225. All right, so it says, so far in this chapter, you have studied the definitions, graphs, and properties of exponential and logarithmic functions. In this section, you will study procedures for solving equations involving these exponential and logarithmic functions. There are two basic strategies for solving exponential logarithmic equations. The first is based on one-to-one properties, which are these two. And the second is based on the inverse properties, which are these two. For a greater than 0, right, and a not equal to 1. The following properties are true for all x and y for which log base a of x and log base a of y are defined. All right, so I wrote those down here. So the first one is a one-to-one property. A raised to the x is equal to a raised to the y if and only if x is equal to y. Now that expression, if and only if, I've probably talked about that before, but it just means you can turn the conditional statement and its converse are both true. By that I mean if I were to reword this and say, if a to the x equals a to the y, then x equals y is true. If and only if means I could say it the other way and it will also be true. So I could say if x equals y, then a to the x will equal a to the y, right? So that's what if and only if means. You could go either direction. Let me say it again. If a to the x equals a to the y, then x equals y. Or I could say if x equals y, then a to the x equals a to the y. So that's what that if and only if means. Sometimes you see that shortened to IFF. So if you ever see IFF, they're talking about if and only if statement. Okay, and that's true for this as well. So log base a of x equals log base a of y if and only if x equals y. Here's some examples for these. So for instance, 2 to the x equals 2 to the y. Since these bases are the same, then the exponents must also be the same. Same way here, your bases here are both e. ln means base e, so then x must be equal to 3. The inverse properties, we've already covered these in the last section. A raised to log base a of x is x. An example of that would be e raised to the natural log of x. Remember, natural log is base e, is 3, therefore x must be 3. And for this one, natural log, which is base e, of e to the x equals 3, therefore x must be 3. All right, so we're just going to go over some of these problems in your textbook. So I'm doing number 2, which is right here. Let's see if I can zoom in on that a little bit. So this is 2 raised to the 3x plus 1 equals 32. All right, so I know that 32 is just 2 to the 5th power, right? Let me just remind you that 2 raised to the 5th power is 32. So I can replace 32 with 2 to the 5th power. So this would be 2 to the 3x plus 1 equals 2 to the 5th power. Now that I've got the bases the same, therefore these exponents must also be the same. So if I want to know x, I could just set the exponents equal to each other. So 3x plus 1 is 5, and solve for x. So that's going to be 3x is 4, so x is 4/3. And I can confirm that by doing 2 raised to the parentheses 3 times 4/3 plus 1, close the parentheses, and I should get 32, and I do. So it works. So x is 32. So notice what I did. I saw it's 2 raised to a power equals this number, so I made that, and it's a textbook, so they're going to, typically this is the way it's going to be. If they give you this number over here, and this is some number, then that means you could rewrite this number as an exponent based on this. I hope that makes sense. Let me give you another example. Let's see. I'll just make one up. So let's say I have 3 raised to the x power equals 9, right? This is a real easy example. And you know that 9 is 3 squared, so 3 to the x is 3 squared. Now that these are the same, then these must be the same. So x is 2. All right. Going back to the textbook, I was supposed to say which of these is correct. Let's see. Determine whether each x value is a solution or an approximate solution of the equation. So x equals -1, obviously not, because the answer is 4/3, and x equals 2. So now I think that what they wanted us to do is plug those numbers in and see what we got. So if I were to do these, the way they're probably intended to be completed, I would do 2 raised to the parenthesis 3 times, and then I put in the number for a, -1, plus 1, and see if I get 32. And obviously I don't, so we know -1 is not a solution. I could try 2, so I'll just hit second enter to pull the whole thing up again and change this to a 2. Delete that. Still not right. So neither of those are solutions, obviously. 4/3 is the solution. All right, so that's how you work these out. Going on to the next section, I guess I should do one with a logarithm, so I'll do 6. Number 6. Natural log of x plus 1, x minus 1, equals 3.8. All right, so the question is 1 plus e, I can't hardly see that. Is 1 plus e3 plus e to the 3.8 a solution? All right. 1 plus e raised to the 3.8. So that 1 plus e raised to the 3.8 minus 1 equals 3.8. Is that a solution? So all I did was I replaced x. Replaced x with what they gave me, which is 1 plus e raised to the 3.8. And then those ones will cancel out. So this is natural log of e to the 3.8 equals 3.8. And yeah, that's true. That's true, isn't it? Because this is the same as this property right here. It's an inverse property, right? But we can confirm it by doing natural log of e raised to 3.8, and it should give me 3.8, and it does. So yes. So yes, x equals 1 plus e to the 3.8 is a solution. All right, and then what about 45.701? Well, let's see. I bet that's probably what this is equal to. What is 1 plus e raised to the 3.8? It is 45.701, so obviously the answer to that's going to be yes as well, right? And notice that has the little approximate symbol here, so yeah. So this is an approximate solution as well, since it has the same value as a. And then 1 plus natural log of 3.8, well, 1 plus the natural log of 3.8 should not be. And it isn't, because the value isn't anywhere near 45.7. There's only one solution here. It's not quadratic or anything. It doesn't have two solutions. All right. So that is the first set. The second set says in exercise 7 through 26, solve for x. So let's look at number 8. So 8 is 3 to the x is 243. And I'm assuming 243 can be written as a power of 3. So let's see. I'm going to just guess. What is 3 to the 5th power? Nailed it. It's 5, right? Just got lucky, right? I got lucky. So let's see. I got some glare here. Let's see if I can get rid of this glare. There we go. It's a little better. Okay. So I can rewrite this. 3 to the x equals 3 to the 5th, which I've just shown you on my calculator here. So therefore x is 5. That's it. That's all you have to do there. So that's number 8. Let's do 12, which is another exponential. 12 says 8 to the x power equals 4. All right, there's many ways to do these. First thing I recognize is 4 is a power of 2, 8 is a power of 2, so I can rewrite 8 as 2 cubed raised to the x. And this is 2 squared, right? So I changed 4 to 2 squared. I changed 8 to 2 cubed. Now, if you remember, these can be multiplied. So this is just 2 to the 3x equals 2 to the 2. So now I know, since I got my bases the same, which is my goal here, that these exponents have to be equal. So 3x has to be 2. Therefore, x is 2/3. All right, so notice what I'm doing. I'm trying to get both sides of the equal sign to have the same base, right? 2 and 2. Started out with 8 and 4. So once you get the same base, then the exponents are equal, and it's pretty easy after that. All right. Let's look at 16. 16 is 2/3 to the x power equals 4/9. Well, if I take the square root of 4, I get 2. If I take the square root of 9, I get 3, which is 1/2 power. So I can rewrite this as 2/3 raised to the x equals 2/3 raised to the 1/2 power. Remember, the 1/2 power is the same as the square root. So if I want to take the square root of these numbers, I could just raise them to the 1/2 power, right? Wait, nope. I'm going backwards, aren't I? This should be 2. Because I want to square 2 to get 4, I want to square 3 to get 9. All right. Went the wrong direction there. So now it's obvious that x is 2. Let's see if I can zoom in on this a little bit. It's a little blurry. All right. So that was 16. What about something like 20? E to the x equals 4. Well, here, whenever you have an exponential, and you can't, there's no way I could write this as base e here. Because e to what power would be 4? There is an answer, but it's not obvious. So what I could do, since this is base e, I'm just going to take the natural log of both sides. So this will be natural log of e to the x, and this will be natural log of 4. So all I did was I took the natural log of both sides of the equation. Now, natural log, which is base c of e to the x, is just x, and my answer is natural log of 4. Right? So to show you, if I put this in my calculator, so I'll do e raised to the natural log of 4, I should get 4. And I do. So that's 20. We'll do 24. So in 24, we've got log base 5 of x equals what? -3. So here I'm going to do something similar. I'm going to make both of these powers. These are going to become exponents on base 5. So I'm going to do 5 log base 5 of x equals 5 to the -3. So all I did was these became powers on both sides. And this is true, right? Remember, this is like one of the inverse properties, I think. One of those properties we covered in the beginning that says that if these are the same, then these have to be the same, right? Okay, so now, since that's base 5 and that's base 5, the answer to this whole thing is just x. So in other words, this whole expression simplifies to x. So I end up with 5 to the -3 power. I can get rid of that negative by just flipping it over. So that's the same as x is 1 over 5 to the 3rd. And 1 over 5 to the 3rd is 5 times 5 times 5. I believe that's 125, right? So this becomes 1 over 125. So that's it. Hopefully this is a review for you. This is still Algebra 2 material. So that's 24. So in the next section it says, approximate the point of intersection of the graphs of f and g, then solve the equation f of x equals g of x algebraically. So we're trying to approximate where the graphs intersect. So I could do that by simply graphing both of these. I'll go to y equal. And for number 28, I'll just put in f of x equals 27 raised to the x. and also g of x equals 9. So this is just 9. I can graph those. I'll hit zoom 6 to get a regular window. Zoom 6. Okay, you can see they intersect right up here. So I could go to second trace intersect, and first curve, enter, second curve, enter, guess, enter. And I get, it looks like 2/3, right? So the intersection right here is 2/3 for 28. Equals 2/3. Okay, so approximate the point of intersection of the graph of f and g of x, then solve. So now we want to set these equal to and solve. So we're going to do graph. And now we're going to solve this equation. So f of x equals g of x. Now f of x is 27 raised to the x. And g of x is 9. And, you know, both these are powers of 3, so 27 is 3 cubed to the x, and 9 is 3 squared. You can multiply these. So 3 to the 3x equals 3 squared. So now we can see that 3x is 2. Right? I'm just looking at that now, ignoring these altogether. I don't need them anymore. So x is 2/3. That's 28. All right, let's see. Next, exercise 31 of 68, solve the exponential equation algebraically, approximate the result of 3 decimal places. Okay, so looking at 32, we have 2 times 5 to the x equals 32. All right, now remember, there's not one way to do these. But there are certain ways that are advantageous. So for instance, the first thing I want to do is get rid of that 2. It's in the way here, right? So I can divide both sides by 2. And that's going to give me 5 to the x, so those cancel, equals 16. All right, now what raised to, x to what power is 16? Well, 5 squared is 25, so it's, I don't know, it's somewhere around 1.5 maybe. I'm just guessing. That's a little too small, so maybe it's 1.6. And all I'm doing right now is just playing around and guessing, trying to get 16. And 1.7 maybe. That's closer. 1.75. Ooh, that's a little too big. 1.74. Better. 1.73. Better. Right? I'm getting close to 16. 1.72 is probably going to be too small, so maybe I just add on a 5 here. Oh, I'm going to have to do like 1.725. Ooh, that's really close. Right, so 1.724. Very close, right? 1.723. It's addicting. That's really close. So the answer is 1.723 approximately. So how do we get that number, 1.723, without all this guessing and checking? Well, we can take, since this is base 5, I'm just going to do log base 5 of 5 to the x equals log base 5 of 16. Now, since these are the same, this is just x. So now I've got the answer, log base 5 of 16. How do you calculate log base 5 of 16? Well, you can use the change of base formula if you've got an old calculator, like this one's an old calculator. It does not have the log base. If I go to math and go down, I don't have that, log with the base on there. So I'm going to use a change of base formula and just do log of 16 over log of 5. And that should give me what the value of this is. And we know that the value should be really close to what I had before, which was 1.723, right? So let's see, log of 16 divided by log of 5. 1.7227. So as you can see, I was on my way to narrowing it down. You could play around with that, but that's it. So this is approximately 1.7227. All right, so let's go back over what I did. I had that 2 multiplied to this exponent, so I divided both sides by that, got rid of it. Now I've got 5 raised to the x 16. There's no way I can make 16 base 5. 5 to what power? I don't know. So what I did was, instead of that trick, I just took log base 5 of both sides, and those just cancel and you get x, and then you have your answer, log base 5 of 16. So that's 32. All right, we'll do something else. Let's do, here on 36, you would just subtract 10 first and then do the same sort of thing. I'll try 40. So 40 is what? That is 4 raised to the negative 3t. Equals 0.1. Okay. Again, I can't make this base 4, so I'm just going to do log base 4 of 4 to the negative 3t equals log base 4 of 0.10. And these all cancel, and I end up with negative 3t equals log base 4 of 0.1. And now I'm going to divide both sides by negative 3. So this is t equals log base 4 of 0.1 over negative 3. Let's see what that is approximately. So using the change of base formula, I'm going to do, for the top, I'm going to do log of 0.1 divided by log of 4. So log of 0.1 divided by log of 4. That gives me about negative 1.661 over negative 3. So now I just need to divide that by negative 3. And it's about 0.5537. So that's my approximate value of t for number 40. We can check it by plugging that number into there. So if I do, let's see, if I do 4 raised to, parentheses, negative 3 times that number, 0.5537, I should get something close to 0.1. And as you can see, it's very close to 0.1. It's 0.09999. All right. So that's confirmation that the answer is correct. All right. I'll look at 40. Let's do 48. 48. Eight raised to 8 times 3 raised to 6 minus x equals 40. All right, what's step 1 here? What should I do first? Hopefully you said divide by 8. So I'm going to divide both sides by 8. That gives me 3 raised to the 6 minus x is 5. All right, so now, now that I've got the exponential expression isolated, I can take the log of both sides. So I'll take the log base 3. Base 3 of 5. All right, now all these cancel, and this just simplifies to 6 minus x. All right, and now I'm going to subtract 6 from both sides. So that's negative x equals log base 3 of 5 minus 6. Now that minus 6, remember, does not go on the argument. So it's minus 6 from the whole thing, not log base 3 of 5 minus 6, right? It's log base 3 of 5, and then once you do that, then take away 6. But this is the opposite of x, so I don't want the opposite of x, I want x, so I need to change all the signs, so I'll make that positive. I'll put that 6 first because it's positive now, and that's minus log base 3 of 5. Okay, and that is your actual exact answer. So this is a correct answer. But if we want to approximate the numerical value of that, we need to do 6, take away log of 5. Yeah, this will be fine, log of 5. You got to keep in mind of order of operations. Order of operations does do division first, so I don't need parentheses here, I don't believe. Log of 3. And I get about 4.535. Right. So let's see if I'll use this one to see if that works. So 3 raised to parentheses 6, take away that number, 4.535, should give me 5. And it does, with round off error. All right. So that's 48. Try to do something a little more complicated here, like 56. So 56 reads 8 times 4 to the 6th. That's 4 to the 6th minus 2x. Plus 13 equals 41. All right, so step 1, I'm trying to isolate what's in parentheses here. So I need to get rid of the 8, need to get rid of the 13, so we'll start with the 13 by subtracting it from both sides. So take away 13. So So this is 8, 4 to the 6, take away 2x. Equals 41, take away 13, which is 28. Now I need to divide by 8. So 28 divided by 8, 3.5. So this is 4, 6 minus 2x equals 3.5. Now I'll just raise both sides. I'll take the log of base 4 both sides. So log of base 4 of 4 to the 6 minus 2x is log base 4 of 3.5. And this all cancels and gives me 6 take away 2x is log base 4 of 3.5. And now it's just a matter of solving for x. If you want at this point, you could, if all you want is the approximation, you can go ahead and turn that into a number. I'll wait to the end. So we'll take away 6 from both sides. So negative 2x equals log base 4 of 3.5 minus 6. Now divide by negative 2. Now when I divide by that negative, it's going to change the sign, so I'm going to put the 6 first. Right, so let me do this. Divide by negative 2, divide by negative 2, divide by negative 2, right? So this is x equals, I'll do this first, that's 3 minus log base 4 of 3.5 over 2. The negative is right here. Right there. All right, so what is this approximately? Let's see. So 3. Let me go ahead and just get this number first. There's a lot going on here. So I'll do log of 3.5 divided by log of 4. It's about 0.9037. 0.9037. Okay. So I'll rewrite this as 3 minus 0.9037 over 2. So I'll divide that by 2. 0.45, about 0.4518. So this is 3 minus 0.4518. So I'm just going to take away 3 from this and ignore the sign. I'm just subtracting in the opposite order. Instead of 3 minus that, I'm going to do that minus 3. And I get x is approximately positive 2.5482. Okay, and this would be your exact answer here. So this is your exact answer. And this is your approximate answer. All right. So you can see these are all pretty simple once you get the hang of it. So that was what? 56. Let's look at one of these division problems. So 62. So it's 400. Where'd it go? 4 over 1 plus e to the negative x equals 350. All right. So you want this off the bottom, so I'm going to multiply both sides by the denominator, which is just going to put it, basically these just switch places. That's the shortcut, right? That goes there and the 350 goes here. Because I'm going to multiply both sides by this, which is going to put it here. And then I'm going to divide both sides by 350, which is going to put that down there. So for the sake of your time, I'm just going to go ahead and switch those. Okay. Now I can reduce that. So 400 divided by 350 is that. I could do math bracket, as some say. 8/7. So that's 8/7. Okay. Now I'm going to take away 1. So 8/7 take away 1 is e to the negative x, right? So all I did was I subtracted 1. Now 8/7 is more than 1. So if I take away 1, that's taking away 7/7, isn't it? So that's going to leave me with 1/7. All right. So now, since this is base e, I can simply take the natural log of both sides. And now, since we have base e of e, I just get negative x for this side. Now I could just switch the signs. So the negative natural log of 1/7 is x. Let's see, what is natural log of 1/7? So natural log 1/7. And then it's already negative. So, but it's the opposite of this. So it's positive 1.9. About positive 1.9460. 1.9460 is approximately x. Here's your approximate answer. How do I know that's right? Well, I could just put it in here and see if that works. So show you a little trick. I'm going to store this number. I'm going to store this in the variable. Let's store it in the variable a. A for answer. Whoops. So alpha math. What I just did was I took this number and I stored it in a. So now if I pull up a, if I do alpha a and hit enter, it should give me that number back, right? So now what I can do is I could just put that number in place of x here. So I'll just do 400 divided by, parenthesis on the bottom, 1 plus e. So second ln will give me e raised to. And then I'll put in that number a. Right? Actually, it's negative, isn't it? So let me insert a negative in here. Okay. And if I did it right, I should get something really close to 350. Cross your fingers. Oh, something in right. So I made a mistake. Oh. So that means I made a mistake somewhere. So I'll have to come back to that. Let's see if I can pause this and figure out my mistake. Let's see. Pause. All right. I think I figured it out. It's just the way I put it in the calculator. Made a mistake. So when I put in the number negative 1.946, I get the right answer, 350 here. I'm not sure what I did. It must have been when I solved for A. Oh, I saved it as a negative. It wasn't a negative, it's a positive. That's the problem. Because the answer was positive, not negative. Now, also, while I was checking this, I forgot that negative natural log of 1/7 is the same as positive natural log of 7, right? So if you switch that to a positive, you can flip that fraction over, which, if you remember, is we learned about that in exponential functions. All right, so x is the natural log of 7. Probably a better way to write it than negative natural log of 1/7, but both are correct. Both are correct. And I do get the correct answer if I put in a positive instead of a negative. I should not have saved that as a negative value. But anyway, you can still save these numbers if you want to. All you do is you do store. Store button is down here. So if I want to have 3.25 and I want to store that because I want to remember it for later, then just so you know, you can hit the store, which opens up that arrow, and then just pick a letter. So alpha B, for instance, right there, alpha B. And now whenever I pull up B, second alpha B, it'll return that value. Okay. All right, so I think that's enough for this video. That takes me through that first whole page, and then I'll do a second video with the rest of the chapter. Hopefully I can get this done in 2 videos. All right, so I appreciate you guys for hanging in there and watching this and taking good notes. We're getting close to the end. After this chapter we'll go into trigonometry, and we'll end on trigonometry, which is a whole different type of mathematics. So if you're struggling with what we're doing now, hang in there because it's all about to change. All right. So God bless you guys. Have a great day. Bye-bye.